Next, and once again, I'm going to apologize for this technical interruption. I'm going to uh, I'm going to proceed. I'm going to invite our next panelist, Mr. Professor Geza Joos from Canada in this moment. Mr. And Professor Geza Joos, he's uh, secretary of the group, the SC6 pillar I talked about earlier. He is professor of the Department of Electrical Engineering and IT Sciences of McGill University since 2001. He has a Cathedra of Industrial Research in Renewable Energies on Integration of Renewable Energies and Distributed Energy since 2009, and a Cathedra of Research from 2004. His research interests are in the power electronics areas and distributed electric resources. He's active member of the SC6 working group. He's also an active member of IEEE in subjects such as STARCOM and Geosystems. He's also a member of SIGREA, of course, and the Academia of Energy.
Presentation today. I hope I completed the introduction of yourself as you enlightened me, and we thank you very much for your contribution to us as SIGRE Chile. It's very important to be always very close to all SIGRE activities in every domain they pursue naturally worldwide. So please allow us to have you on board with your presentation.
So I'm very happy to be able to present on battery energy storage. I do regret not being physically present, not being able to meet you people. I didn't understand what you were talking about because I don't know Spanish, although my wife keeps on saying that I should learn it because it's extremely important because she likes chili. Anyhow, this being said, I will present the findings of working group C30 on battery energy storage. The tutorial that will be presented is not specifically tailored to the Chilean context. It is essentially one that we've been presenting a number of times now at different SIGRE sessions and conferences. Do I have to share my screen?
Yes, please.
Okay, I'll do that. I'll open up. Let's see this, how I do this. Do you see my screen?
Yes, we see your screen.
The title. So it's a C6 tutorial, and it deals with distribution. We do realize that storage at this time, it's probably because of an economy of scale and because of the benefits, is mostly being installed today at the transmission level and connected to the transmission or sub-transmission grid. This presentation deals with distribution, but many of the concepts are transferable to transmission, particularly when you go to grid services. So it is divided into sections, and we'll go through each of these. So it has to do with the technology, the benefits, planning, grid codes, and impacts. So first of all, the structure of a battery energy storage system is classical or conventional. Let me just do this here. So the batteries are behind the DC to DC converter, and then there is an inverter connected to the grid. This essentially makes the battery energy system very much from the grid perspective, similar to what you have for wind turbines and solar farms. It's a grid inverter grid interfaced system. We'll come back to that later on. So very simplified, this is a mechanical equivalent of battery energy storage. So you have stored energy, you have losses, and you have a control. And the difference between this and a mechanical system is it's electrical system. So there's not only P, real power, but there's also reactive power. What is important in this figure is the notion of losses. One of the critical issues with battery energy storage is that not only do you have the capital expenses, the CapEx, but you also have the operating expenses, which are maintenance, but also losses. So if you look at a battery energy storage system from which you can retrieve 80% of the energy stored, you have to take that into consideration when you design or make a business case for storage. In terms of storage, there's a large number of different options available, which are summarized here. The technologies evolve, but fundamentally, the concepts remain. There is a notion of operation, duration, and there's notion of power. And the product of time and power is energy. Today, the dominant technology is lithium-ion, probably because it is a transfer from transportation technology. The problem with lithium-ion is that long-term storage is difficult to achieve, not like pump storage. And this is a limitation to the technology when it comes to having long-term storage. In other words, storage that can cover a day or half a day, like for solar power, or storage that can go weekly or seasonal or even yearly. So what is interesting here is, apart from lithium-ion batteries that are essentially short-term or medium-term storage devices, having pump storage at the crux here, they're the largest ones and the longest duration. You do have other types of batteries that people are talking about quite a lot these days, particularly flow batteries that people are trying to revive. And you've got then all the other types of chemical type batteries, the lithium-ion family, and many other types that people are coming out with, including metal air batteries. So the impacts, these are taken from national laboratory documents in the US, and this is Sandio National Lab. So it combines essentially the benefits and the cost, because everything in any type of installation is a cost-benefit analysis or results from a cost-benefit analysis. So what you have here on the right-hand side is the benefits. Power quality and reliability is one of them. Investment deferral, system capacity, energy time shift, frequency regulation. At this time, at least in the US, if anybody wants to make money, the best way to make money is in the area of frequency regulation. Unfortunately, in frequency regulation, you're talking about large amount of power, gigawatts, and typically you have to be connected to the transmission grid. Otherwise, there's no impact in terms of frequency regulation. So when you say that individual electric vehicles will do frequency regulation, it has to be aggregated to make any sense. The least beneficial, or the application that is the most difficult to justify in terms of benefits is power quality and reliability. It's very difficult to put a cost on power quality, and even more difficult on reliability. Investment deferral is a short-term benefit, and we'll come back to these benefits later on. But the purpose of the presentation is not to analyze benefits, because the difficulty in analyzing benefits is having the data, and every situation is different. On the cost side, you have the physical element, which is the battery itself. So battery cell and packaging. Some of the cost is power electronics, although the cost there is decreasing and the cost of batteries is also decreasing. There is an issue of balance of plant, and then there are the operation and maintenance costs. And if there is a cost to recycling, it has to be added to the overall cost of deploying a battery energy storage systems. This is a slide that was put together by ABB, and that shows the different benefits that can be possibly quantified for battery energy storage. So you have from the short term, millisecond, which is grid stabilization, frequency regulation, short-term frequency regulation, and power quality. Then you have spinning reserve, standalone islanding, benefit storage, smoothing, capacity firming. That is extremely important in wind and solar. The problem there is that it is essentially smoothing out the variations and not filling the voids. Peak shaving, this is load shifting. Peak shaving and load shifting are in the same category. This is an important benefit. So this is a summary. Now, what is important in this slide is that, yes, batteries can provide all these benefits, but they cannot provide them simultaneously. So you have to decide what your priority is at a given time and put the battery energy system to use for that particular application. So here are examples of what the battery can provide in terms of benefit. This is typical of an islanded system that runs a diesel and has solar panels. So, but the battery essentially smooths out the diesel power, and so it essentially allows the load to be met with a combination of variable power, which is PV power, and a diesel engine, which tries to run at constant speed. So in the middle of the slide here, you have a situation where the diesel is turned off and the system runs or is fed from a combination of PV and afterwards a battery. So in the middle of this scheme there, the PV power is very large, middle of the day. There's enough power there to not only feed the load, but also recharge the battery. And then when you move further down, the PV disappears, and you have to rely on the diesel or the battery. There's a comment here very important, and it applies to countries that have a lot of solar power, California in particular. It's difficult to manage the decrease in solar power. It all happens at the same time. It's called the duck curve. You can see it here when the solar disappears, and you have to start up your other generation. And you can see here that the diesel has a very steep ramp rate associated with the disappearance of a large amount of PV. This is another example of battery energy storage benefit, a revenue stream, which is associated with frequency regulation. The battery energy storage essentially allows you to regulate the frequency within the band. Here it's a 1 Hertz band. by providing energy when the frequency drops and by absorbing the energy when you have overgeneration. And as I mentioned, this is the revenue stream in the US that brings you the most amount of money and sometimes allows you to justify installing battery energy storage for the other benefits, realizing that the frequency regulation is a short-term request from the system operator, so the rest of the time the battery can be put to other uses. This is another example of battery energy use. So what you have here is peak shaving and void filling, and then you have the short-term frequency regulation or frequency following. So here it's more a question of short-term frequency regulation than actually frequency support. And this is another example of application, and it's been tried in Canada in particular, the US as well. When you have an overloaded substation, what you can do is add batteries that will supply the load for the short term, let's say morning and afternoon peaks, and that may justify the use of battery energy storage system. The only problem there is that if the substation load it will increase in the future, then this is just a short-term solution to a problem. Now let's look at the battery energy storage system in the grid. So this is an example of a microgrid, grid connected. And the role of the microgrid here is essentially to firm up renewable generation, which is not dispatchable, wind and solar, and may be used also to do load management. Having a battery in a microgrid is beneficial also when you have an islanded operation, because a battery energy storage system can serve as an anchor and as the reference generator. The only problem there is that if the islanding lasts a long time, let's say a couple of hours or days, then you have to rely on dispatchable generation such as CHPs, combined heat and power, or diesel generators. So there's the issue of long-term battery energy storage operation. As I mentioned at the beginning, the battery energy storage system is interfaced with the grid using an inverter, which is the same one as you would use for wind and PV systems, the same one as you would use for other energy storage systems such as flywheels and what people were pushing in the past, which is other types of storage systems, such as superconducting magnet energy, which is a very short-term storage. So what the battery energy storage system has, because of the presence of the inverter, you have complete power and reactive power control. You can provide reactive power and real power independently, and then you can put into the inverter all the intelligent functions that you would need. So these are the common functions. They're defined in a number of IEC documents. They're also defined in an EPRI document. EPRI started the term common in function, intelligent function, comes from an EPRI document. And it includes a whole slew of functions like volt-var, volt-watt, frequency watt, and then the write-through voltage and frequency functions. And again, the issue here is that you cannot accumulate functions. You have to decide a priority order and which ones you will implement. An example of intelligent function is one that is featured in the latest IEEE 1547 standard for DER interconnection. It's essentially a function that limits the voltage when you have overproduction and supports the voltage when the voltage drops below the minimum value. So specifically for the battery energy storage interface, what you have is a battery. You have a DC to DC converter to allow you to operate optimally the system. In other words, maintain a constant DC bus irrespective of the battery voltage. And again, you have P and Q control. This graph here shows you that the battery energy storage is probably the most versatile type of a generator, quote, generator load. It can operate in 4 quadrants. It can operate as a load, as a generator, so positive, negative P, and it can also provide reactive power, capacitive, and inductive on demand independently of the P. The only restraint or limitation is that you have to respect the kVA rating of your inverter. You cannot go beyond that. And inverters typically have no short-term rating, maybe 150% short-term. So you're limited strictly to the kVA rating of the inverter interfacing the battery energy storage system. This is a list of the parameters of the battery energy storage system. I will not go through this. Now, the operating mode, I did mention some of them, the intelligent functions. The other thing is that the battery energy storage, like any wind turbine generator or solar system, is typically synchronized to the grid using a PLL. Then you can operate either as a grid following mode, which is the typical mode of operation for solar and wind, which is PQ controlled injection. What is being talked about very much these days is grid forming inverters, which are supposed to be similar to synchronous machines. They're virtual synchronous machines if you want to program them like that. The only problem is that there is no inertia to speak of. You can emulate an inertia with a battery energy storage system, but you have to program the function. So the present use of grid forming modes is an islanded operation, as I mentioned, and there's a big talk about the future potential of grid forming inverters in systems where the amount of synchronous generation is going down, and particularly when you go to 100% renewables. So this is an example of battery energy storage configured as a virtual synchronous machine. And the key problem here is to get the proper function and the proper parameters to emulate the synchronous machine. Whether this is a solution, again, is not obvious. The role of the battery energy storage system is important in the context of the DSO TSO interaction, particularly everything to do with grid operations. I won't go through this. The important thing here is that either you put the battery energy storage together with a solar farm, and then you have a firmed up generator, or if you have individual batteries at the grid edge, you have to probably use an aggregator to make them useful. Planning considerations. So I will essentially go very briefly through this because I'm running out of time. You will have the slides so you can have a look at them. And if you have any questions, feel free to send them to me. So as I mentioned, and this is just a summary, the battery energy system has a steady state operation like any device and a transient operation. The steady state operation is defined by the inverter and by the stored energy, and these are the things that I mentioned before. Inverter kVA rating efficiency. By the way, efficiency and losses are extremely important, and one of the big issue with flow batteries are the important losses, store and retrieve. There are limitations to how you can operate the battery, and they're usually dictated by the battery management system. You're limited in the charge and discharge rates because that will affect the lifetime of the battery. You're also limited in the number of charge and discharge cycles, at least today. There are batteries, people claim, that have 100,000 charge discharge cycles, but typically this is not the case. And now planning, I will not go through this, but there's a whole issue of how do you size the battery, and that has to do with what the battery does. And so this is an example of primary frequency control. You also have, you can size it for peak shaving, and then you have to size it for the maximum power that you need. And you have to then decide on the kilowatt rating, and you have to decide on the kilowatt hour rating. And there are many examples where the kilowatt and the kilowatt hour are not the same. They're the same if it's a 1 hour rating, but anything else is possible. So here are a list of sizing constraint, primary frequency control, accounting for load growth, and so on. One of the important issues today is a life cycle assessment, because we're accustomed in power grids to have equipment that lasts up to 50 years, if it's a line, even 100. Substations, transformers, 30 years, probably breakers as well. And here we have an element that we do not know the life cycle of, but it probably doesn't go beyond 5 or 10 years. The business models, again, I did mention that you have to justify the deployment of battery energy storage systems. So you have to quantify the benefit, you have to make a business case. So you have to have revenues associated with the battery energy storage system. Ownership is a big thing because you have to interact with the grid. Some of the installations are DSO owned, distribution system operator, third-party ownership is possible. This is all a very open question. Local energy community. Market participation, the US has opened the market recently through a FERC order 222 to distributed energy resources, including battery energy storage system. They've mandated the TSOs to open the market for these devices, individual or aggregated. So that's why there is an important role today for aggregator. Grid codes and standards. So in terms of grid codes, the battery energy storage is simply a distributed energy resource. In other words, it can operate as a generator, it can operate as a load, and it's fully controllable. So all the standards that have been created for DER should in principle be applicable to BES, battery energy storage system, with adjustments made for the fact that the mode of operation can change from motoring to generation or from load to generation. So there are steady state features that we did mention. Provision of reactive power and real power. And then there are the transient operating mode, which are similar to that of the DER. You have to be able to do low voltage and high voltage right through, and low voltage and high frequency right through. And there are a very large number of standards. In the US, the much talked about standard today is a 1547 2018 version. So these are examples of voltage and frequency right throughs. The number of levels depends upon the grid code, and the values also depend upon the grid code. For example, in Quebec, the low voltage right through has to be at least 5 cycles and 0 volts, which is an extremely stringent requirement, which means essentially that the inverter has to be configured in such a way that it keeps a reference voltage for the duration of the 0 volts. So you do it through the PLL, you freeze the PLL, to the previous value, hoping that when the grid comes back, you come back at the proper phase angle. Frequency right through, again, depends upon the utility. In Quebec, we have very wide frequency ranges because it's an isolated system. So this is a list of standards applicable to battery energy storage in the US. It's all in the 2030 series, which is the Smart Grid series, and they were the first ones to address battery energy storage issues. And this was followed by a standard for microgrids and a standard for DERMS, which both of them involve battery energy storage systems. Then you have the grid codes for DER, the 1547 2018, and there's a new project being in the process of approval, which is 2800, which will be a standard for transmission system interconnected DER, including battery energy storage systems. And then you have the whole slew of standards, European standard in the 61850 collection. So integration consideration, I already mentioned most of these. Important is the protection studies and the impact studies. Harmonics shouldn't be an issue because they're inverters and harmonics are well managed. It's an important issue today, the notion of being able to combine storage systems of different types. For example, one combination that is used in a number of applications is battery energy storage plus flywheels. The flywheels being able to supply impact loads and the continuous load supplied by the battery. Impacts and benefits. So you have two sets of impacts, those at the distribution and the transmission level. In distribution, we already mentioned most of these, distribution upgrade deferral, power quality customer side, voltage regulation, peak demand reduction, customer time of use energy pricing. The customer can install a battery energy storage to take advantage of time of use pricing, and demand side management. And on the transmission side, the list of benefits are the same, plus those that are associated with operating transmission systems, which are frequency support regulation and reserves, and also black start. There are projects in the UK in particular that aim to use DER for black start. In other words, black starting local areas and then connecting them together to restore the power grid. On other considerations, so this is a big talked about issue in the US, justifying battery energy storage using multiple value streams. Doing just one value stream doesn't seem to make a business case. So they look at things like frequency regulation, which is at specific times, and then the streams that I mentioned before. One of the more important benefits is firming up variable and intermittent renewable resources. Today, solar farms are very often associated with battery energy storage system. It's not yet the case with wind turbine or wind farms. Storage as a non-wires alternatives is much talked about. It's very similar to investment deferral. It's managing conjuncting. And there's a much talked about topic, which is locational value of BES, and CGRE C6 has a working group on this. Now, here are deployment example, and this is the end of my presentation. So these are just a list of recent projects, and you can see that they're mostly connected. They're mostly large projects. There's an economy of scale issue here. There's very little done at the distribution level. So you're looking at 30 megawatts or more. And what is also interesting is the applications. So the first one is flexibility services, or so it's a whole slew of services. Capacity issues, particularly in California. The virtual power plant is a very popular topic in Europe, particularly in Denmark and areas around that. And islanded operation is one of the big application also of battery energy storage system. And you can also see that you have a difference between megawatts and megawatt hours. So this is an island, and the battery is used to supply power to the island when you have an n-1 contingency, in other words, loss of a line or overloading of a line. There is a case study of EPRI that is published, publicly available, and it does a study. It's a study, and the key benefit, the highest value is regulation and system capacity. So best practices. So I did talk about the business case. The impact on reliability and resilience is very difficult to quantify, particularly if you have a distribution grid that has a very, very high reliability, one interruption in a year, things like that. It's very difficult to justify adding equipment just for that. Integration with electric vehicle charging station is coming now, particularly fast charging stations. Life cycle assessment has been around for a long time. Battery repurposing has been talked about for many years now. One idea is to use them in substations when they have a degraded life. And one of the important issues is that the battery energy storage system does not replace a generator because somebody's got to recharge it. The practical consideration, and I did mention most of these, the important thing is that today, when you look at battery energy storage systems, you have to look at alternative approaches that might be cheaper, like demand response, curtailing renewables. Important also is to take into account the OPEX in your business case, cost of operations, and ownership is a big issue. So experiences, and I did mention already these, applications, the performance, the important thing about battery energy storage, like any equipment, is that it has to be tailored to the specific location. So altitude is important, climate is important because you have to cool the batteries. You have to have a battery energy management system, which is typically supplied by the battery manufacturer and may limit what you can do with the battery. And then you have the whole issue of mean time between failures. In the case of a mean time between failures and operating experience, I don't think we have enough experience of battery energy systems to come up with a value for the MTBF. So this is the end of my presentation. There is a list of documents that I used or we used to prepare the tutorial. So thank you very much for your attention. I don't know how the organizers want to handle the rest of it, and if there's time for questions. I barely made it.
I'm sorry, I was muted. Thank you very much, Professor, for this thorough presentation. Your presentation naturally is very important to us since it naturally provides a context for all these group, basically, and the technologies we would like to study and the applications naturally. So we invite you to stay connected, hopefully to the end of this module, because we will be sharing questions to yourself so that at the end of everyone's presentation, we will talk to the audience, and we'll share all their concerns and interest, basically. So thank you very much.
And I thank you very much. I hope that I didn't go too much overboard, and that the message is reasonably clear as to the benefits and limitations of battery energy storage systems.
Thank you very much for that.